let's take a look at our notes. Let's start up here. When the outcomes in the sample space of an experiment have the same chance of occurring, the outcomes are said to be equally likely. Equally likely outcomes. So this is an example. These are in fourths. They're all the exact same size. So each one of these different sample spaces are equally likely. Over here, these are not equally likely. Why are they not equally likely? Right. Some of them are larger. That means that there's more space, and so there's a greater chance the spinner is going to land on something when there's more space. If there's a little tiny space, there's not much room for the spinner to land. So it would be less likely for that to occur. All right. The theoretical probability of an event is the ratio of the number of ways the event can occur to the total number of equally likely outcomes. That's the theoretical probability. That's in theory. What do you think will happen? So we call that one the theoretical. That's like what we were doing when we were using and we were making a fraction. So up here, if I could see the different colors, this one right here is red. So what is the probability this spinner will land on red? So it is the ratio of the number of ways, 1, 2, 3, 4 ways, that an event can occur to the total number of equally likely outcomes. So what's the fraction that this would land on red? What do you think, Hattie? 1 out of 4, 1/4. We could write that as a decimal. That would be 25 hundredths. And as a percent, what would that be? 25%. That is the theoretical probability. That's what we think would happen. Now, what would happen if I actually spun the spinner? That's called the experimental probability because I have to run an experiment. Okay? So, you need to know that theoretical probability is based on a math problem, a fraction. The number of ways that an event can occur, so there's one red, to the total number of equally likely outcomes, there are 4, so 1/4. An experiment in which all outcomes are equally likely is said to be fair. It's a fair experiment. You can usually assume that the experiment involving coins and number cubes, which are dice, are fair. Okay? This one up here would be fair. Would this one be fair? No, because one of the sample spaces is smaller than the other. All right. Finding theoretical probability. An experiment consists of rolling a number cube. So it wants you to find the theoretical probability of each outcome. Note the word experiment doesn't necessarily mean you are looking for the experimental probability. All right, so we are finding the experimental. What do we think is going to happen on a number cube? So if we have a dice, how many sides are there? 6. There's 6 sides on a dice. How many of those sides would be a 3?
1.
So what is the theoretical probability of rolling a 3? 1/6. 1 out of 6. I could turn that to a decimal and a percent if I needed to, but it doesn't tell us we need to. So, what is the theoretical probability of rolling a number greater than 3? How many numbers are greater than 3 on a dice? 3 out of 6. Should we simplify that? 3. Okay. If we're getting ready to go into 8th grade and then we're a year away from high school, should we be simplifying fractions?
Yeah, we should.
Yes. So 3/6 simplifies to 1/2. Thank you. So your answer would be 1/2. 1/2 of the sides on a number cube would be greater than 3. All right. What's the theoretical outcome of rolling an even number? So what are the even numbers on a dice? 2, 4, 6. So 3 out of 6. And that simplifies to 1/2. And what is the theoretical probability of rolling a number that is a multiple of 3? What are multiples of 3? So 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is 9. So how many multiples of 3 are on a dice? 2. 2 out of 2, 6. And does that simplify?
Yes, it's 1/3.
Yes, that simplifies to 1/3. So 1/3 of all the sides on a dice are a multiple of 3. All right, so probability sums. So the experimental probability, if you are flipping a coin and if you run an experiment and you flip the coin 3 times, it would land on heads. In this experiment, it landed on heads 3 times. So that's 3 out of 10 times. And then in that same experiment, of those 10 times, 7 times it landed on tails. So all of those, the 3/10 and the 7/10 should add together and make 10/10, which is 1. So this was running an experiment. Is that what you would have thought theoretically would have happened if you flipped a coin? So you would think that there's a 50-50 chance. So we would predict that half the time it would land on heads and half the time it landed on tails. So that is the theoretical probability. So do these match, the experimental and the theoretical probability? Do they match? Is 3/10 the same thing as 1/2? And 7/10 the same thing as 1/2? No, it's not the same. So you have to know that there's a difference. Now, the more that you run an experiment, the closer it should get to the theoretical probability. So flipping this coin 10 times is probably not a good indicator. If you run an experiment, you probably need to flip it more, like 50 times or 100 times. And the more you flip the coin, the closer you're going to get to the theoretical probability. So that's an understanding that you need to have. So if you're going to run an experiment, you probably need to do more than 10 trials to try and get a probability. So the sum of the probability of heads and the probability of tails is 1 or 100%. This is because it is certain that one of the 2 events will occur. It is certain. So your probabilities always need to add up to 1 or 100%. All right, any questions about anything on this page? All right, let's look over here. Let's move to the other half of this page. All right, we talked a little bit about this the other day on the skills practice that we did, the problem where it was windy and there was a 12% chance that it was going to be windy. So what was the chance that it was not going to be windy? Do you remember? It was 88%. Okay, so that is called, if I know that it's 12% chance it's going to be windy, its complement is 88%. And so how did Cameron know that it was 88%? What's the math he did, Eilish? 100%, because the 2 events have to add up to 100%. It's certain it's either going to be windy or it's not going to be windy. Those are our only 2 choices, windy, not windy. And so there's 100% chance that it's either going to be windy or not windy. So that is called the complement. That is a vocabulary word that you need to know. The complement of an event is all of the outcomes in the sample space that are not included in the event. This symbol, and it kind of looks like an apostrophe, that means complement. The symbol can be used to indicate the complement of an event. The sum of the probabilities of an event and its complement is 1 or 100%. An event and its complement have to add up to 100% because the event will either happen or not happen. So this is the math problem. The probability of the event plus the probability of the complement of the event always equals 1. So let's find probability by using the complement. Let's try these problems. Number 1, the weather forecaster predicts a 20% chance of snow. What is the probability that it will not snow? And then this means right here, let's look how to read it, the probability of snow, but what does this little apostrophe mean right there? The complement. So if you see that, it's not asking you, it doesn't say that there's a 20% chance of snow, so what's the probability of snow? It's what's the probability of the complement of snow? Just because of that little apostrophe, and I'm going to try to highlight that. This little mark right there means the complement. So if it's a 100% chance it's going to snow or not snow, and then they're forecasting 20% that it will, what's the probability that it won't? 80%. So the math that we do to prove that is 20% plus 80% equals 100%. Does that make sense? All right, let's look at the next problem. The probability of spinning an even number on a spinner is 45%. What is the probability that you will roll an odd number? So that looks like this. The capital P means probability of rolling the complement of an even. Anybody know? So it's 40. Is it 55?
Yeah.
Okay. It's mental math. Good. So I would have had to say 100% minus 45%, and that equals 55%. So my answer is 55%. All right, let's look at the last one, number 3. The probability of winning the raffle is 0.005%. What is the probability of not winning? The probability of the complement of winning. Now, is this a big number or a small number? Small. You're not very likely. The probability of winning the raffle is not very high. So, what do I need to do with this one? What do you think, Eileen? 5,000? And what did you get? Okay, so let's all do that. Let's say 100% minus decimal 005 equals, let's all do that on our calculator, please. Bless you. So, and do I need to use the percent sign, or am I just doing 100 minus? Just do 100 minus decimal 005, and you get 99 and 995 thousandths. 99 and 995 thousandths of a percent that you will not win. So I would say that participating in that raffle is probably not a good use of your money unless you are a very lucky person. All right. Sally and Lorena were discussing how to write the probability of rolling a 3 on a numbered die. Sally writes it as 3/6. Lorena writes it as 1/6. Who's right and who's wrong? So a 3 on a dice. Who's right and who's wrong? What do you think, Eiley? Lorena is right because why? There's 1 3 out of 6 sides. Find the theoretical probability of each outcome. Write your answer as a fraction, decimal, and a percent. So what is the theoretical probability of randomly choosing a B from the letters in algebra? How many B's are in the word algebra? There is 1 B. And how many total letters are there? 7. 1 7. Let's change 1 7 to a decimal. So we say 1 divided by 7. Good morning. It's okay. Let's round that to the nearest hundred. So that 2 tells the 4 to stay a 4. So we're going to call that 1400ths. And so as a percent, that is 14%. Make sure you write the percent sign. All right. What is the theoretical probability of rolling a factor of 10 on a number cube? A factor of 10. What are factors of 10? 1. What else? 2 and 5. 1, 2, and 5. So that is how many? 3 out of... How many sides are on a number cube? 3 out of 6, which is 1/2. And 1/2 as a decimal is 5/10. And 1/2 is equal to what percent? 50%. Number 3, the probability that it will be sunny is 15%. What is the probability that it will not be sunny? 85. So I'm going to call that 8500ths. I'll call that 8500ths and 85%. So if we knew it was 85%, should we be able to work back to this fraction? Yes. A spinner is numbered from 1 to 10. What is the probability that you will spin a number less than 5? What numbers are less than 5? 1, 2, 3, and 4. So there are 4 numbers less than 5, and how many on the spinner in total? 10. So that's 4 out of 10. 4/10 is 4 in the 10th place. And what is that as a percent? 40%. This should be easy from all the work that we've done on fractions, decimals, and percent since the beginning of 6th grade. Rolling a number that is 2 or greater on a number cube. 2 or greater. So how many sides are a 2 or greater? 2, 3, 4, 5, and 6. So 5 numbers out of 6. 5, 6. I don't know the decimal for that, do you? So I need to say 5 divided by 6. 83 hundredths, and the 3 is repeating. And so that's 83%. All right. Any questions on how we did anything on that page? And you all understand the complement, right? Okay. All right. We'll put that to the side. We'll put them in our notebook in just a minute. Let's put that one to the side. Application questions. All right, so here's where we're going to apply what we know. A fair coin is tossed 50 times. It lands on heads 28 times. What is true about the results of the experiment? So we're running an experiment. So theoretically, if we flipped a coin 50 times, how many times would you expect it to land on heads? We would say about half, and what's half of 50? 25. So we would expect it to land on heads or tails 25 times. But when they ran the experiment, it landed on heads 28 times. So we're going to answer some questions about what really happened. What is true about the results? The coin landed on heads fewer times than expected. No. The coin landed on heads more times than expected. Yes. The coin landed on heads the same number of times. No. The results cannot be compared with expected results. No. We could figure out a theoretical probability. So your answer is B. All right, let's look at another situation now. Mario has a bag of marbles. You're going to hear this whole marble thing a lot on tests and questions. They like to put different colored marbles in a bag and have you find the probability, which is going to be kind of what we do with our jelly bean experiment. Mario has a bag of marbles. In the bag, 6 were blue, 5 were red, 7 were green. What is the probability that Mario will randomly pull a blue marble from the bag? So theoretically, what do you think is going to happen? So the first thing I need to do is I need to figure out how many marbles are in the bag. 18 marbles are in the bag. How did I know that? We said 6 plus 5 plus 7 equals 18 marbles. And how many of those are blue? 6. So the probability is 6 out of 18, or 1/3. 1/3 is our probability. So now we are going to take that and make a prediction. If Mario selects 60 marbles out of the bag, how many times would you expect him to pick a blue marble? So we're still not running an experiment. We're still making a prediction. So we can take this, if we know 1/3 of them are blue, then we could say if he chooses 60 times, how many of those times should he choose a blue marble? What's the math we do here? Cross multiply. 6 times 1 is 60. 60 divided by 3 is 20. So we would predict 20 blue marbles. And this is one of the areas that we didn't do so well on that last test, was that prediction. So we're still working on that in this unit. All right, now we've got this spinner. Does this look like a fair spinner?
No.
Does everything look like it's about evenly sliced?
Yes.
I think it does. And there are 5 total outcomes. So what is the probability, looking at this spinner, of spinning and landing on an even number? What do you think, Malachi? 2 out of 2 out of 5, or 2/5. So we know the probability. So now it says if you spin the spinner 200 times, what is the best prediction possible for the number of times you would land on an even number? So we know that 2 out of 5 are even. So if I spin it 200 times, how many times should I land on an even number? Okay, so 2 times 200 is 400. And 400 divided by 5 is, Ethan, what did you say? 80. So our answer would be 80 times. If you wanted to spin the number 3 10 times, theoretically, how many times would you need to spin the spinner? So this one's a little bit different. Let's find the probability of landing on a 3. What's the probability of landing on a 3? 1 out of 5. Now, it says we want to land on the 3 10 times. How many total times do we need to spin? So we know that we want to land on the 3 10 times. There's 1 3. We want to land there 10 times. So how many total times do we need to spin the spinner? Do you see 50 times? Do you see how I knew to put the 10 in the numerator? Okay, so 50 times. Because 5 times 10 is 50. 50 divided by 1 is 50. 50 times. What is it, Malachi? Well, this is theoretically what would happen. Okay. Now, do we know that the experimental does not always agree with that? Yes. Dane wrote the letters of New York City on cards and placed them in a hat. So each letter was on a different card and he put it in a hat. He selected a card and replaced it every time. That's important because if he took a card out and set it to the side, then that's going to change the number of cards in the hat. Do you understand what I'm saying? So if you draw a card, you can't put it to the side. You have to put it back in, shake it back up, and then draw another card. All right. If Dane did this experiment 88 times, what's the best prediction for how many times he would choose a Y? So we need to decide what's the probability of choosing a Y. How many Y's are in the word New York City? Really?
No.
2. 2 out of how many total letters are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 words. So if he did the experiment 88 times, how many times would you predict he's going to choose a Y? Where does the 88 need to go? The numerator or the denominator? Denominator. That's the total number of times. So I could cross multiply, or I could say, how do I get from 11 to 88? Times 8. So I could do this times 8, and I would get 16. 16 times. Cross multiplying also works. Any questions about that one and how I knew to put the 88 in my denominator?
Yeah.
How did I know? Because it said if he did the experiment 88 times, how many times would he choose a y? So the y was here. So if I was looking for the y again, it would have to be here. So that's what I was looking for, so that's how I knew. Does that help? Okay. All right, let's move on to the next page so we can wrap these notes up. Yvette used the spinner shown. Write your answers as fractions and percent. So, A means what's the probability of landing on an A, and B means what's the probability of landing on the, what's that mark mean? Complement of A. So what's the probability of landing on an A on this spinner? 4 out of 6, which simplifies to 2/3. So we're writing as a fraction and a percent. So to turn that to a percent, I say 2 divided by 3. So let's round that to the nearest percent. So it's 66% or 67%? 67%. So what would be the complement? So that would be 1/3, right? Because 2/3 plus 1/3 is 3/3, and so that should equal 33%. Because 67% plus 33% needs to add up to 100%. Jose spins 45 times. How many times would you expect him to land on an A? Aaron spins 240 times. How many times would you expect him to land on a B? So let's deal with C. How many times do we expect him to land on an A? That's 2/3. And so if he spins 45 times, how many times would you expect it to happen? 45 times 2 is 90. 90 divided by 3 is 30. So this is C. Let's do D over here. How many times would you expect Aaron to land on a B? A B is 1/3. So if he spins 240 times, 240 times 1 is 240. 240 divided by 3 is 80. All right, is this making sense to you all? Okay. 5. Brianna flipped a coin 20 times. The coin landed on tails 7 times. How many more times would she have expected the coin to land on tails? So, she flipped it 20 times, and it landed on tails 7 times. So, how many times would you have expected it to land on tails? 10. So, that means we needed to add 3/20 to get 10/20. And so 3 more times is what we would have expected. Number 6, if Henry rolls a number cube 48 times, how many times would he expect to roll a 5 or 6? So, how many numbers are a 5 or a 6? 2 out of 6, and that simplifies to 1/3. So if he rolls 48 times, how many times should he land on a 5 or a 6? 1 times 48 is 48. 48 divided by 3, 16. All right, any questions? So we'll get to practice with this. I don't know that we'll get much practice with it today. I don't even know that we're going to start this skills practice today. We'll probably hold on to that till tomorrow since you don't have homework on Wednesday. But let's go ahead and get this in our journal quickly before it's time to leave. We've got 5 minutes. So it appears 132, 133, 134, and 135 are all going to be devoted to theoretical and experimental probability. So take your pages, cut them in half, or fold them. The first page we did in our notes should be the first one that you glue in to the first 2 pages. Yes.
I don't have any pages left in my
I don't know what we'll do. Let me think on that. Do you have any pages after the little pink tab? Do you have that in yours? You already used those? Huh. I don't know. We're so close to the end that I don't know that it would pay to start a new one. Well, we'll finish this unit before spring break, and then we're all done learning new math. Then it's just a review for the rest of the year. I know. Thank you for checking, though. I do forget. All right. So, should be 132 and 133. 134 and 135. And so then in the front, I'm going to list those pages as theoretical and experimental probability. And then once you get that glued in and you get your table of contents up to date, you can get everything put up.